The only regression model that we study in AP statistics is a linear regression model. We only talk about how two variables relate linearly. But occasionally we know, especially if we had a course in pre-calculus, that sometimes we have functions that relate non-linearly, like an exponential function, right? What if this is what if the best model to make a prediction is one that's exponential, meaning we'd have some kind of predicted value of y, but the way that it relates to x is that we have some kind of base value raised to the x, right? Sometimes variables behave that way. Or sometimes we have maybe the predicted value of y is best predicted by what we would call a power function. This is one where maybe you have a coefficient, a x is your base, but it's raised to a power. Maybe it's a quadratic, maybe it's a cubic. Okay, so this is an exponential model. And this is the power model. All right, and I want to talk about how we can write these as linear equations. So if an exponential model is our best fit or a power model, we can still use a linear equation, and how those logarithms will relate to each other is a pretty important concept for us. So some basics about what we mean when we talk about the language of logarithms. When I read this, log base b of a equals c, right? Log base b of a equals c, okay? That basically means that if b is my base and c is the exponent, it's going to equal a. So it means that c is the exponent that I would raise b to in order to get a. So what I always try to tell my students when I'm teaching logarithms, or if they're having questions about it, a logarithm is just an exponent. When you see a logarithm, realize right away that that's an exponent. So when I come down here and I want to solve some of these logarithms, log base 2 of 8, remember this is an exponent. What I'm saying to you is that this is an exponent. So we basically have two main bases that we function with when we're talking about logarithms in most of our practical settings. One is Euler's constant, 2.718. If you took pre-calculus, you have a better understanding of what that means. But it's a number really similar to pi that occurs really often in a lot of applications. So often that probably more useful than the base 10 logarithm. So when we just see log, that's called a common log with no number written, no index for a base. We assume it's a base 10 because that's how we count our numbers. And then base e is Euler's constant number. So if I see a situation like this, natural log, so remember natural log means log base of e. So this is saying to me, what exponent would I raise e to, right? What exponent would I raise Euler's constant to in order to get e squared? And when I pose it that way, it's really easy to see it would be 2. And that's one of our basic rules for logarithms, that if we have the same base and same log base, they will cancel each other out. So here we're saying if we have a log of base 10, we just understand 10 to be there. What power do I raise 10 to in order to get 100? And we can see that that would be 2. And then finally here we're saying to ourselves, again, it's a base 10, there's nothing written. What would I raise 10 to in order to get 1/10? And hopefully we remember our negative exponents, that would be -1, because 10 to the -1 is equal to 1/10. So one of the things that we really need to be able to do is take a situation where we have an equation, we want to make a predicted value. So in this case here, we have natural log of y hat, but what we want to do here is predict what y hat is. So, and I want to do this when x equals 2. So how would I do that? If I just plug 2 in here, right, a common mistake that my students will say is they'll just go like this, 15 plus 3 times 2. They'll do 15 plus 6 and say that that's 21, and that's going to be incorrect. Okay, you have to just know enough about logarithms to know to plug into this. You're going to say that y hat, since this is the natural log of y hat actually equals e to the 15 plus 3x. That's all I need you to be able to do with an expression like that. And then we would easily be able to use that to make our prediction. So this would be e to the 15 plus 3 times 2, which would be y equals e to the 21st power. And at that point, we would use the calculator for that. Okay, just plug into the calculator to finish that off. Same thing over here. What's happening here? We have y hat equals e to the 15 plus 3 natural log x. Okay. And then we would plug x in here. We'd have to use natural log twice. We take the natural log of 2 and get a decimal, multiply it by 3, and then use the calculator again to finish that off. So this is essentially what we need to be able to do with our logarithms. And then keep in mind two kind of fundamental rules here in terms of linear relationships. Okay, if the log of y and x relate linearly, then x and y relate exponentially. I'll give you a really very basic example of this. Here is a situation where I have x and y, and I'm going to have them relate exponentially, right? So when x is 1, okay, so I have when x is 1, 2, 3, and 4, I have y is 10, 100, 1000. So hopefully you can see the relationship here is that y is actually equal to 10 to the x. That's an exponential situation. Well, think about what would happen with the log of y now. What's the log of y? Well, if y is 10, the log of 10 is just 1, right? 10 to the first is 10. What's the log of 100? It's 2. The log of 1000 is 3, and so on. So notice what we have then. We have this list and this list. If we graph those, we would have a straight line exponential or straight line linear relationship between those two. And then in addition to that, so that's sort of rule number 1 when it comes to our log situations. If log y and log x, so notice I took the log of both of those, relate linearly, then x and y relate in a power model. So that would mean that by power model, we mean that the best model for that situation would be a times x as your base raised to some power p.